Okay, I want you to try a little thought experiment with me. It is a hot afternoon, maybe you've just come back from tuition, and you are just extremely thirsty. You walk into the kitchen to make a drink.
I like where this is going, a nice cold drink.
Exactly. Now, you see two containers on the counter. One is a tiny little teacup, barely holding, say, 100 milliliters of water. The other is a massive 1-liter water jug. Now, imagine you take exactly 10 grams of sugar, 1 big tablespoon, and you dissolve it into that teacup.
Okay.
Then you take another tablespoon, exactly the same amount, 10 grams, and you dissolve that into the big jug.
All right, so just to be very clear, the amount of the sugar is identical in both cases, 10 grams each.
Perfectly identical.
Yeah.
But here's the puzzle. If you
Well.
take a sip from the teacup,
Ah.
it's practically syrup. It's overwhelmingly sweet,
You'd probably make a face.
for sure. But if you take a sip from the jug, you might not even taste the sugar at all. And that's the question I want to start with. Why? Why does that happen?
It's a great question because it's a classic intuition trap. We think the total amount is what matters, but your tongue isn't a weighing scale, you know? It doesn't count the total number of sugar molecules. It senses how crowded they are.
How crowded they are. I like that phrasing. The crowd.
Think about it, no. In the cup, those sugar molecules are packed tight. Like a Mumbai local at 6 p.m., they're constantly hitting your taste buds.
Right.
In the jug, they're just floating around. It's like a Sunday morning in a huge park. They are lost in all that water. And that concept, measuring this crowd, is exactly what we're covering today in our deep dive into Unit 1 solutions.
And the specific topic is expressing concentration of solutions.
That's the one.
So for the Class 12 students listening, why should they care about this? I mean, beyond just make it a good glass of Nimbu Pani.
Well, this is basically the alphabet of physical chemistry. You can't write sentences if you don't know your ABCs, really.
Good point.
If you don't understand concentration, you can't solve problems on vapor pressure later. You can't do osmotic pressure. You definitely cannot handle chemical kinetics.
So that's the absolute foundation.
It's the language of this entire unit. Plus, you know, in the real world, this is how pharmacists make sure a medicine cures you instead of poisoning you. It's how industries mix chemicals safely. It's even how we do stoichiometry. Everything comes down to expressing concentration correctly.
Okay, so let's get into the core idea then. If we just strip away all the formulas for a second, what are we actually doing when we express concentration?
At the simplest level, really, concentration is just a ratio. That's all it is. It's a way of asking how much solute is dissolved in how much solvent, or in how much solution.
So it's kind of like a recipe for making chai.
It is precisely like a recipe. You might say, I need 2 cups of sugar for every 5 cups of flour. That's a concentration. But in chemistry, we have a bit of a problem with that.
Because cups aren't very precise.
Exactly. And make it sweet is subjective. Science needs numbers. It has to be rigorous. So imagine a chemist's recipe. Instead of cups, we might say, add 2 moles of salt to 1 liter of solution.
And that is what we call molarity.
Correct. Or we could also say, add 2 moles of salt to 1 kilogram of water. And that would be...
molality.
Yes.
Okay, pause for a second there. You just said molarity and molality. They sound almost identical. I mean, 1 letter difference. Molarity with an R, molality with an L.
And that's Finn. That is the biggest trap for students in the board exams. They sound the same, but they measure the ratio in fundamentally different ways. This is the misunderstanding trigger we see all the time.
I really want to fix that confusion right now before we go any further.
Yeah.
Because I can just see a student panicking in the exam and misreading the word.
It happens. So here's the key distinction. Molarity, with a capital M, uses the volume of the total solution.
Okay, so the solute plus the solvent. Everything together.
Everything in the flask, yes. Now, molality, with a small m, it uses the mass of just the solvent.
Just the liquid part.
Correct. It ignores the solute entirely in that denominator part of the calculation.
That feels like a very subtle distinction. I mean, why do we even need both? It seems a bit redundant.
It feels redundant until you start changing the temperature. This is where it gets really interesting. Imagine you have that flask of solution, the one based on molarity, so on volume. Now you heat it up. What happens to the liquid?
Well, any liquid expands when it gets hot. That's basic physics.
Right, the kinetic theory. The molecules get excited, they push each other apart, and so the volume of the solution increases.
But we haven't added or removed any salt.
No. The number of moles of solute, that stays exactly the same.
So, if the top number of the fraction, the moles, stays the same, but the bottom number, the volume, gets bigger.
The total value of the concentration drops. A 1.0 molar solution that you made at 20 degrees Celsius might actually become a 0.98 molar solution at 40 degrees.
That's actually really annoying for an experiment.
It's a nightmare for precision. Imagine doing a delicate experiment in a lab that doesn't have good AC. Your numbers would keep changing just because the room got hotter in the afternoon.
So this is where molality comes in to save the day.
This is exactly where it comes in. Because molality divides by the mass of the solvent. Does heating water change its weight?
No. A
Yeah.
kilogram in hot water is still a kilogram. Mass is conserved.
Exactly. Mass is independent of temperature. So molality is, you could say, temperature proof.
Ah, that makes perfect sense now.
And that's why if you look at questions on freezing point depression or boiling point elevation properties that always involve changing temperature, we use molality. Always.
It's not just a different definition. It's a functional necessity.
Precisely.
So if I have to give the strict insert-safe definition, the one I can write on my exam paper for full marks, what would that be?
Okay, the anchor definition you should remember is this. Concentration is a quantitative measure of the amount of solute dissolved in a given amount of solvent or solution, and it is expressed in various units, like molarity, molality, mole fraction, or percentage.
Quantitative measure. That's the key phrase there. We are putting a number on how crowded it is.
Exactly. We are quantifying the crowding.
Speaking of crowds, I love this analogy from our notes. Comparing concentration to measuring the density of a crowd in a room. I think this helps visualize why we have so many different units. Can we just walk through that?
Let's do it. So imagine a big wedding hall filled with people. The people are the solute particles, and the hall itself is the solution.
Okay, picturing it, a crowded hall.
Molarity. Molarity is like counting people per room. You count everyone, and then you divide by the total volume of the room. It tells you how crowded the 3D space is.
Right, so if I pour a bit of the solution, I know how many moles I'm getting.
Yes. But now, think about molality. This is like counting people per acre of floor space. You're measuring the floor, which represents the solvent, without worrying about how much space the people themselves are taking up.
Okay, molarity is the 3D space, molality is the supporting floor. That helps. What about mole fraction? That one comes up a lot too.
Back to our crowd. Mole fraction is like asking, what fraction of people in this room are wearing hats?
Hats?
Yes. It doesn't care about the room size or the floor area. It's just a pure ratio of numbers. Out of every 100 people here, 20 are wearing hats. So the mole fraction is 0.02. It's a proportion.
And what about percentage?
That's the simplest. It's just like saying what percent of this room is filled with people versus how much is empty space.
This really explains why this whole concept exists. Historically, before they standardized this, chemistry must have been, well, a mess.
Oh, complete chaos. Imagine, it's the 19th century. A chemist in England writes to a chemist in Germany and says, I made a strong salt solution. What on earth is strong? A pinch of salt. Is it saturated?
It's like saying add some masala. My mom's version of some and my version are very, very different.
Exactly. Without these standardized units, molarity, molality, and so on, chemists couldn't communicate properly. They couldn't scale up reactions for industry. You couldn't make medicine safely. These units are the standard protocol that lets science happen everywhere.
I want to try a mental movie to really lock this in for everyone listening. So if you can, just close your eyes for a second. Obviously, if you're driving, please don't.
Let's set the scene.
Picture a clean white lab bench. On it, you have exactly 1 mole of salt. That's about 58.5 grams. A neat little pile of white crystals.
Okay, I can see the pile of salt.
Scene 1. We're making a molar solution. You take a volumetric flask, that glass one with the long neck and a thin line on it. You put the pile of salt into the flask. Now you start adding water. Keep pouring, watching the water level rise until the bottom of the meniscus just touches that 1 liter line.
And notice something critical here. The salt crystals themselves take up some space, right? So you are actually adding slightly less than a full liter of water, but the total volume of the whole mixture is exactly 1 liter. That is 1 molar.
Got it. Okay, reset. Scene 2. We are making a molal solution. You
Right.
have your pile of salt again, but this time you put a beaker on a digital weighing scale and you press tare to zero it out. Now you pour in water, carefully, until the scale reads exactly 1,000 kilograms.
See the difference? Here, you have a full kilogram of water plus the 58.5 grams of salt. The total volume will be a little more than 1 liter. This is 1 molal.
Perfect. And finally, scene 3. Mole fraction. Just imagine a pie chart floating above the bench. One slice of that pie is the salt. All the other slices are the water. We're not measuring volume or mass. We are just asking, how big is the salt slice compared to the whole pie?
That is a perfect visualization. If you can keep those three scenes clear in your head, the flasks line for molarity, the weighing scale for molality, and the pie chart for mole fraction, you will never confuse them.
Let's bring this back to some real-world examples now. We started with that sugar-water taste test.
Right, and that observable phenomenon that is purely molarity in action. Molarity tells you how many sugar molecules are in each milliliter. When you drink from the small cup, the high molarity means millions more sugar molecules are physically hitting your tongue's taste receptors every second.
That's literally a bombardment of sugar.
Exactly. Your tongue is a chemical detector. It's detecting the concentration, not the total amount in the container.
What about a technology application? Where do we see this outside the kitchen or the lab?
Hospitals are a major one. Think about IV drips. Next time you see a saline bag or a glucose strip, look at the label. You'll often see something like 5% WV.
Which stands for weight by volume, correct?
Yes. It means 5 grams of glucose have been dissolved to make 100 milliliters of solution.
Why do these percentage there? Why not molarity? Isn't molarity more scientific?
It is for reactions. But percentage is much safer and easier for logistics. It scales perfectly. If a nurse uses a small 100 milliliter bottle, they know it has 5 grams. If they use a big 1-liter bag, the ratio is still the same 5 grams for every 100 milliliter.
So it reduces the mental math they have to do in a hurry.
Exactly. It ensures the patient gets a safe, consistent dose regardless of the container size. It helps eliminate calculation errors in a high-stress environment.
That makes a lot of sense. Now, I want to bring up a counterintuitive example from our notes. We touched on this, but let's dig a bit deeper. You might think molarity and molality give you basically the same number. No, because the density of water is around 1. So 1 liter of water is roughly 1 kilogram.
And for very dilute solutions like your tap water, yes, they are very, very close. If you calculated both, the numbers would be almost identical. But
Here it comes, the butter.
But for concentrated solutions, they start to drift apart, far apart. Imagine a thick syrup or the concentrated sulfuric acid we use in the lab. The solute, the acid in this case, starts taking up a lot of space.
Because there's just so much of it.
Right. In a concentrated solution, the volume of the solution is much bigger than the volume of the solvent alone. So molarity, which is divided by the large solution volume, and molality, which is divided by the smaller solvent mass, start giving you very different numbers.
So the assumption that M is roughly equal to M is actually dangerous.
It is dead wrong for concentrated solutions. Never assume they're interchangeable in an exam problem unless the question specifically states a dilute aqueous solution.
Okay, before we get to the summary, we have to talk about the one formula that every student uses in their lab practicals, usually 5 minutes before the examiner arrives.
Oh, yes. You must be talking about the dilution formula, M euro. M.
That's the one. I know I've just plugged numbers into it, but I usually just memorized it. What is actually happening there?
It's actually just common sense disguised as algebra. Think about it. You have a bottle of concentrated acid. Let's say it's 10 molar. That's your M euro. You pour out a little bit, say 10 milliliter. That's VO.
Okay, so inside that 10 milliliter, there is a certain number of acid moles.
Right. Now you take that 10 milliliter and dump it into a bigger beaker. You add a lot of water. You now have a new volume, V, and a new lower molarity, M euro. But, and here is the key, did you add any more acid molecules?
No, I just added water. The moles of acid are the same.
Did you take any acid out?
No.
So the moles of solute you started with must be equal to the moles of solute you ended with. And since moles is just molarity times volume.
Ah, so amiro is just initial moles, and imiro is final moles. The equation is just saying the moles don't change.
Exactly. It's just the law of conservation of moles for dilution.
That makes it so much less scary.
Just remember the catch, though. This strictly works for molarity calculations when you are just adding solvent. Don't try to use it for mixing two chemicals that react with each other.
That's a very good warning.
Oh,
Okay, we have covered a lot. Let's bring it home. Let's do our exam-safe clarity lines.
this is the part where you might want to grab a pen. These are the key definitions that get you the marks.
Let's do them one by one. Number 1, molarity.
Molarity, capital M, is the moles of solute per liter of total solution. And the tip here is to use this for stoichiometry and any volumetric analysis in the lab.
Number 2, molality.
Molality, small m, is the moles of solute per kilogram of solvent. Tip: use this when temperature is changing, like in freezing point or boiling point questions. Remember, mass doesn't change with heat.
Got it. Number 3, Mole fraction.
Mole fraction, the symbol is chi, is the moles of one component divided by the total moles of all components. And remember, this is unitless. It's just a number, a pure ratio.
Okay. Number 4, percentage.
This can be mass by mass, WWW, volume by volume, V, or mass by volume, WV. The key tip is to always read the question carefully to see which units they want. Don't just guess.
And finally, number 5, the dilution formula.
That's MRV arrow. This connects the initial and final states. But remember, it only applies when you're diluting something by adding more solvent.
That's a solid cheat sheet. So let's wrap this up with a short summary. If someone is walking into their exam, what are the 3 or 4 main things they absolutely must remember?
First, the core idea. Concentration is simply a measure of how crowded the solute particles are. It's a ratio, just like a recipe.
Second, keep that crowd in a room analogy in your head. Molarity is the crowd in the whole 3D room. Molality is the crowd measured against the floor space, the solvent's mass.
Third, remember the practical applications. The IV drip in the hospital, the chemist dealing with temperature changes. Using the right unit matters for safety and for accuracy.
And finally, the golden rule for the exam. Watch your denominators. Molarity uses liters of solution. Molality uses kilograms of solvent.
If you mix those two up, you lose the marks. Solution versus solvent, volume versus mass. Just keep them straight in your head.
Well, that brings us to the end of this deep dive. This is the foundation of Unit 1, so make sure you are really solid on this. Once you master this language, things like solubility and vapor pressure will make so much more sense.
Absolutely. Build this foundation strong, and the rest of the chemistry building will stand tall.
Thanks for listening, and good luck with your studies.
Happy learning.